Welcome everyone. I'm very happy to be here today. First, I want to thank the organizers for letting me giving this presentation for you. So, as I was introduced, I'm from Poland. I'm working at the university with staff connected to fluid dynamics. And because of my interest in NVScene and computer graphics, I also do some research in real-time fluid dynamics, and this is what I will be talking about. But because we are at the NVScene event, today I will be presenting as a Maku floppy from NVScene group where I work or I play or have fun as a coder. So I'm a programmer doing all the programming stuff in demos. And hopefully the title remains as it was. So how did I become interested in fluid dynamics at all? Because this is actually a very hard topic, and although it's very fun, very funny, and we've seen a lot of interesting stuff in computer graphics happening around, so you may get interested because of it. It is nice as it is, but it is a hard topic. So I became interested not because of the hardness of it, but because of the pictures. And this is a few slides from few scans from the work from Los Alamos laboratories, where the free surface flow was first studied in using computers by Harlow, Welch, and all the very famous T3 group. So what you see here on the left hand side is a picture which actually made a lot of change in my professional life, because when I've seen this for the first time, I said, come on, I want to see this moving. And that was a time that it was not possible to actually see everything around in the internet. Also, the original papers that this work was based on were not available. They became available in 2004 by publication from the Fluid Research Journal. But so I said, okay, let's try to see how it works and how to implement it. And I had no idea about Navier-Stokes or equations at all. So what you see here is an effect of a liquid drop splashing into a deep pool with some jet effect. On the right-hand side, there is a compressible case. So I wanted to see that. Where this was my interest, nowadays I work more with porous media, with very complicated geometries like you see there. So this is three-dimensional sphere packing made of impermeable spheres. These are those black parts. And what you see, these lines are streamlines of a fluid, incompressible fluid flowing through this system. So it's extremely complicated for computational codes to actually compute this if you use traditional Navier-Stokes solvers. And so for this, we use something else I will be more talking about later. So these are porous media. They are large. They are parallel. We use parallel codes for that, and actually these are all long runtimes, so not really real time. And to have real-time solutions, I will speak about three things. First, I will give you some short review of real-time fluid dynamics that is already available around. So you've probably you are aware about the keynote today, which didn't make this presentation easier. Actually, so we have plenty of methods about where we have solutions to fluid dynamics. This is the marker and cell method from Los Alamos I told you about. The one which is more real-time from Josh Stamm, very famous solver, probably most of you know about it, and the smooth particles hydrodynamics, okay? And this will be just for a short review. Then I will introduce the Lattice Boltzmann model that was used in my demos before. So this is a model that actually gives you the possibility to simulate the fluid in matters of solving Navier-Stokes, not directly, but using grids instead of famous and commonly used particles nowadays. And the third one will be aerodynamics. So I will be speaking about the things like many objects flowing around in a bulk flow. So what I want basically to have is a solver which gives you, which is easy, understandable to ordinary programmers, which gives you actually a fluid-like effects in the interactive frame rates. And this is the third part. So to actually start with fluid dynamics simulations, we have to start either from above or from the bottom in terms of the scale. So if we go from below, from the bottom, we have something like a molecular dynamics. You imagine that if you have a fluid in a container, I don't know, in a glass of water, for example, all the fluid consists of individual particles. If we know the forces between all these individual particles, there is a physical theorem that you may actually predict what is the behavior of this system. And this is called the Laplace demon. It is a fact that if we were able to solve the very basic Newton equations for this system of particles, if we knew the basic interactions on microscale, we would be able to get macroscale effects like splashing flows and so on. The problem is, of course, that is very difficult for the today computers. The other way is to solve the Navier-Stokes equations. These are nonlinear equations for the fluid flow. I will also speak about this today. So again, from below there is molecular dynamics. So this is the picture. We have many individual particles, but there is too many atoms required if we want to achieve effects like, I don't know, wind tunnel with a car inside, okay, Audi car inside, the self-driving Audi car inside, okay, with a fluid flowing through over this car with all the turbulence effects. That would be just too much, even though we are actually there at this conference also to see solutions for that. But there is another way. There is Navier-Stokes equations, and I will not be speaking very much about details, but what is important there is to know that these equations are, this is not one equation, these are two. One is for the momentum, one is for conservation of mass. And so the equation above, there is, you may think about it as about an equation which actually is analog to Newton's law. You have an acceleration part on the left-hand side, so it's like A, okay, is equal to force divided by mass, and this is on the right-hand side. So if you know all the forces and the pressure, you calculate from, so P is the pressure. If the pressure you have from your solution, you have velocity, which gives you possibility to compute the viscosity effects, and you have the external forces, okay, like gravity or some other force. And so if you, on the left-hand side, you have acceleration, there is unsteady part, there is a convection, and so the goal of Navier-Stokes and of solving this equation actually is to get the velocity field. If you get velocity field, you solved the fluid dynamics problem, okay? You solved it, you may do whatever you want with your field. So if you have this velocity, you may put some particles, you may put some objects, you may see how all this flows around, you may solve some density solution or something. This is Navier-Stokes. And now to make the picture complete, and I would be very happy if someone didn't know and will end up after this talk knowing this one, that there are two main approaches to fluid dynamics or to description of fluids actually. One is Lagrangian, this is how we call it in physics, and one is Eulerian. The Lagrangian approach is one with particles, so that everything in the fluid moves with individual particles and properties are advected by these particles itself. And the other one is Eulerian, where we have this computational, sorry, not computational, but we have fields of velocities and densities and pressures and everything, so that the properties of fluids are advected within the flow. And these are two approaches. And about these two, I will be talking today. So the key work I want to mention, because not only because of my interest, but afterwards, after I worked a lot with that, works from Harlow, Welch, Shannon, and Daly from Los Alamos, are papers about the marker and cell methods. This is because historically, these are one of the first approaches successful approaches to simulate the free surface flows and all very complex behavior of fluids with computers. So this was 1965 when the paper, the Los Alamos report about the Mach method was published at Los Alamos, and somewhere in 1990, somewhere in 2001, I remember, Los Alamos gave a free access to all the reports they published within years. It was available on the internet. Nowadays, it is not possible, but I was lucky enough to have this access. I downloaded these papers. So what you see there on the left-hand side is a scan I did just before this party. So this is a scan of report which consists of complete solver for marker and cell method, described with very nice and fancy diagrams made by these people. By the way, they are very famous in this community, I think, if there is anyone from fluid dynamics, so they are known. And then, so just a few words about the method. It would be a long talk if I wanted to go more deeper, but what is the key points there are, so the method works on Eulerian grids. We describe the grid as, the very basic version of it works on the rectangular grid. We have a boundary, fluid, free, or partly boundary and fluid cells. And we keep the solution on the grid in a staggered way. That means pressures are inside of the grid cells and velocities are on the edges. Why do I mention this? Because this way one can get the very nice accuracy of the solver just by keeping these primitive variables on the grid in this way. So this way, by simple discretizations, we get the second order accuracy, which is important point there. And so how does the Navier-Stokes translate in the marker and cell method manner? So the marker and cell is explicit solver, so it discretizes Navier-Stokes directly to the grid. I just drawn it in for all those who didn't ever see the solution to Navier-Stokes equation. It is transferable to the computational code directly. There is algorithm behind. What I wrote there is just discretization of Navier-Stokes. To solve with the marker and cell, you have to apply the special algorithm. So you do this like few times, okay, and do several other things with the fields. But anyway, what is important is that all this inertia, forces, pressure, and viscosity parts are translated into a staggered grid in this way. All these half indices might be easily translated into full indices by a simple mapping. So this is not a problem. So as you see, we directly discretize this equation on a grid, and we apply this special procedure. The procedure works like this. So just in words, because I didn't prepare it in the slide. So it's we solve the momentum equation. We get the wrong answer, so we get the wrong solution. This solution is not incompressible. Using some equation for pressure, we get a pressure correction which is blocked by this block of impermeable cells. We open the gate at some time 0, and then it's basically because of the pressure difference between this and these points, there is a force acting in this direction. So what we see is the creation of this interesting thing. So now you may run your imagination 3D with fancy shaders, with everything, and done in more modern way. So the very fundamental thing we have a solution to the flow, okay? And now there is an example of the marker and cell solver in how does it move. So this is non-real time, done for some other projects by me, but this shows the very much the capabilities of the solver. So on these velocity fields, what we do is we track these marker particles, and those are showing us the fluid behavior. So what you may notice there is what is the most important about the methods which are originating from Navier-Stokes from above, is that we actually get the solution in entire space. So we get a solution in a bulk flow. And this is really interesting because we see all these vortices happening around and there is nothing put by hand. So we didn't put any vortex model or anything, turbulence model like that. This is just a solution to simple Navier-Stokes, incompressible Navier-Stokes equations. And so in 1996, because there were, of course, people who wanted to bring this to computer graphics community, there was a very famous paper from Nick Foster and Dimitri Metaxas, who basically did present a method to simulate the free surface flow. So it was 2D and 3D with some, so the original paper was in 3D only in the axisymmetric flows. And so what they basically did was they sold marker and cell method to computer graphics community. And it was a very, very good step they did, and it is wonderful because then it made a lot of interest in fluid dynamics from this time. So it is a very important paper worth to remember and worth to see. It's available on the net, you may see. So Nick Foster. And a few years later, Nick Foster with Ron Fechtke from Stanford University did make a work about to improve the solver they presented in '96. So they put some, instead of particles, they put some level sets to actually see the surface evolution in the flow in 3 dimensions in more accurate way. And they also made some modifications to the solver. So instead of using explicit discrete time steps, they used the so-called the backward procedure to get the large steps, which basically ruins the accuracy of the solver, but brings it more into applications in computer graphics. And one of very nice, interesting applications was the mud shower taken by Shrek in one of the first movies from PDI. So it's an application, and now you see where did it originate from. So you see the larger context. But how about real time? So I talked a lot about fluid dynamics and history more. Okay, now you see the history, but how to bring it real time. So in 2003, there was a paper by Josh Tam, not one. So this person made a lot of effort to sell the method, and he succeeded because it's well known. It's a method to simulate the Navier-Stokes solution in real time. And there were many papers. One was stable fluids, about not real time, but about the solution itself. But there was also a paper, real-time fluid dynamics for computer games, as far as I remember the title well. So it's a very nice work. You may be very excited seeing the easiness of the solution there. I mean, not easiness, but the way it is presented. There is a result. So key points about this thing is that this solver is short. It is a complete procedure, which gives you actually very similar to what was done in marker and cell method, but it's different in terms of numerical procedures applied. So there are some more high math involved, but it's also straightforward to implement. So it's a short. So the computational code presented by Josh Tam is like one page of paper in C code. It's stable, means you may get as large time steps as possible. Okay, at this picture it might be not that beautiful, but again, people did make a lot of effort to make it in 3D, and also Josh Tam presented it. So what is important, you get all these vortices and so on. But there is a problem. It is dissipative. That means you take large time steps. It is real time, really real time. So it found its applications in real time environments. But it's dissipative, means you get all the smoke effects, but not really the fluid effects. So with fluids, it's much more complicated. And to solve the fluid problems, it turned out none of those two is really successful. So neither Navier-Stokes nor molecular dynamics was able to give us solutions in interactive world. Sorry. So there were people working in this field and in these problems, and they created something in between. So they put something in between of molecular dynamics and Navier-Stokes. hydrodynamics. Again, the picture is like that. We have individual particles, but these are not particles like we know from molecular dynamics. These are not particles of fluid. These are representative particles for a kind of a bulk of a fluid. So they represent more larger part of a fluid than single particle. So you may think of individual particle as a smoothed density of density distribution of a particle. So you approximate a single particle by like a bell-shaped curve, okay? Now, if we think about it in this way, we may now solve the Newton equation as in the same way we do in molecular dynamics I showed before, and solve the Newton equations and move all these particles around. And this gives us a very straightforward, I mean, very direct picture of the solver. So we basically have particles which represent the fluid, and we don't have to advect anything else in the flow. So the solution itself, which is within these particles, gives us a way to see the fluid flow, okay? This is different from a Eulerian approach where we have a velocity field and we have to advect something, okay? Now, so this is the smooth very basic smooth particle hydrodynamics solver. So we have at the beginning we have this column of water filled with particles. This is on purpose. I did it in the way that you see all these particles because each of these particles is actually the bell-shaped part I showed you. So this is the solver, the very inside of the solver. And so we see all the effects like splashing and so on. This is actually, being there at this conference is maybe worth to mention. This is a very simple CUDA implementation without fancy optimization or anything at all. This is just the very basic solver was put into a CUDA kernel. And it works very fast, so it was not necessary to optimize it for this little application. And so what we do in smooth particles, we have another equation which is representative of, it is a Lagrangian way to write the Navier-Stokes. So again, on the left-hand side, we have acceleration. On the right-hand side, we have forces. There is this pressure, viscosity force, and the external force. And so I don't want to describe, and because this is a lot of work, but to do the lecture about this equation. But what is nice to remember is it's much easier than Navier-Stokes. You don't have the incompressible part, another equation for incompressibility, which actually makes it also trouble there. But anyway, there are some improvements on this. But anyway, this is simpler, and it translates to Newton law we know. And I will skip at this, okay? Smooth particles, you may see everywhere. You may hear about it in the computer graphics community. It is very nice. It has some succeeders. You have the point-based methods and so on and so on. This is okay. But there is another one. And because of my work, I became interested in so-called Lattice Boltzmann method, which is somewhere else, somewhere in between Navier-Stokes and smooth particles, because this is also solution to Navier-Stokes in an Eulerian way. And I want to show you the capabilities of Lattice Boltzmann to simulate in real time. Now, we start with the very famous person. So in 1844, Ludwig Boltzmann was born, who did invent many things in his life. He's very famous in physics. But one of his greatest inventions was the kinetic theory of gases. And it's actually a very sad story because he committed a suicide, and one of the reasons was his depression he described about his work. So it turned out many, many years later that he became very, very famous, which is also worth to remember. And so what is the kinetic theory of gases? There is one thing to remember about kinetic theory gases I am able to really give you a few words about today. It's a distribution function. So instead of velocity field we had, instead of particles, we have something in between. So what Ludwig Boltzmann did was he connected the microscopic world where we have these individual particles with macroscopic world where we see all the movement of fluids and of gases in macro scale. he connected it with distribution function, which is basically a function which tells you how many particles travels in a given direction in the space, okay, in a given point in this space at a given time, okay? Nothing more, just like that. So it's a kind of histogram of velocities that is described in entire space. So it is a fundamental thing, but with this function, we are able to actually, with this function, we are able to describe our system as something complete. Having distribution function for entire system, we have all the velocity fields, density fields, and so on. Because you may easily understand that calculating a sum of distribution function gives you, for example, density. Okay? So now, how about, so if we agree that distribution function is our solution, there is a equation of the dynamic evolution of this distribution function given by Lattice Boltzmann, which is the Lattice Boltzmann equation, which basically consists of two parts. One is the time and the kind of convection derivative of the function in space, okay? And on the right-hand side, we have a collision term. And now I will skip all the theory part, which is actually a lot of work. Since something like 25 years, there is a lot of research going on Lattice Boltzmann. You may have heard about it. But so all this happens there in between of these two lines, okay? Going from this equation to this part, or going from cellular automata to this part, it's kind of problematic. But where does it end up is this simple discrete equation of evolution in the simplest case with single relaxation time collision term. So what we have is an evolution of density function, which you may put on your grid, okay? You have a discrete grid, you put some velocity directions, and you solve this equation. This is nothing more. You have the function value at the next time step, at some kind of the direction ahead of you have the value of the function at the previous step, you have it again, and you have some, okay, the equilibrium function, which is basically another equation taken from Maxwell-Boltzmann distribution. So this is, for a moment, a black box, but you may take it from the simple statistical physics book. Okay, nothing fancy. You get the velocity fields, you may calculate FEQ. If you take this one to work, you may actually solve the fluid problem. And the very basic Lattice Boltzmann code, I have some slides afterwards. If someone wants to see, I can show it later. But so very basic Lattice Boltzmann solver, which is actually complete Navier-Stokes solver, is like a half of a page of the C code. And this would be very nice if someone keeps it in mind after this talk and maybe try to implement by himself or get some code from the internet. But so this is how the Lattice Boltzmann is described in two-dimensional space. So we have a grid. At each point in a grid, we have this distribution function. Again, distribution function is a function which is basically a histogram of velocities. So all these F0, F1, F7, in this particular case of Lattice Boltzmann, of course, because this is the one model, there are more with more velocities. There are values of velocities which are distributed like this. And now we solve the problem I shown you before. Now, so what effects we can get with Lattice Boltzmann? So we may solve the problem of a fluid flow through some geometry. We basically take our discrete grid, we put some geometry in, and we get the fluid flow solution. And there is an example. So I got the effect from crash demo here to show you how the Lattice Boltzmann work in this environment. We took some photo from the internet. It actually was treephoto.com, actually, something like that. But it is not easy to make a picture like this. Then we cut part of it just to take some geometry, and we binarize it for Lattice Boltzmann and added some simple stuff there. And now, so let's see geometry like this, where the black part is impermeable for fluids. So all the black thing will be not permeable. There is a white part which is permeable. We fill it out with a fluid and we push a flow through. Okay, we apply some pressure, or at this particular case, this was gravity force. Now, if we do that and put some particles, which actually will represent the fluid flow, we will see how this evolves in time. And this is the real-time solution for the problem on the right-hand side, with geometry given on the left-hand side, given in interactive frame rates, done in single CPU. So there was no, at this time, I was not involved in any GPU work with computer graphics. We did it on a single CPU, and it works like this. So you may see a lot of potential in that method for the flows like this. And worth to mention also, because I am aware that this is not three-dimensional and so on, but what is worth to mention, the nice capability of Lattice Boltzmann there is, what is shown here, is that it works pretty nice for complex geometries. So this geometry is really complex in terms of solving Navier-Stokes with the traditional solvers. It might be really, really hard to solve the system of equation for discretized Navier-Stokes in this. So just to give you some more reasons to become interested in the method, there is also research going on simulating the moving boundary conditions, which are hard for all the solvers around. Also, smooth particles doesn't give you simple solutions for it. So on the mesh of Lattice Boltzmann, you may easily get some interpolated values, as you may see from these pictures. You may, let's say this black curve is a kind of boundary. We want to have a velocity equal to 0. So for that, you will have to get some inverse procedure to get these points equal to 0. You have to change the velocities inside of the object. And there is a paper from 2007 which describes a very simple method to compute the moving boundaries in Lattice Boltzmann. And again, because Lattice Boltzmann is it's a nearly incompressible solver, it gives you possibility to put velocities inside by hand. So you may put some corrections to velocity fields to get moving boundaries. And there is an example how it works within our codes. And there is, so again, the real-time solution for the moving boundaries in Lattice Boltzmann, moving in interactive way. If you remember from Bremen intro, it was Breakpoint 2011, I guess, and or 10, there was a fish-like object moving like this in part of it was 64 intro. And there is another one we didn't use anywhere, but and again, what you see is CPU solution, because at this time we were also not implementing it for GPUs, but it gives you interactive response from fluid flow. And how about LBM and GPU? I repeated many times that these were not GPU. So Lattice Boltzmann scales very well on GPU, and this is something that if you go for LBM conference, you may be very happy, because there are many people also mentioning and describing Lattice Boltzmann as a method to that gives you nice speed ups on GPUs. And there is a plot of the speed up of Lattice Boltzmann code given in terms of on the right hand side, on the bottom, on the x-axis, you have the number of lattice grids, okay, lattice points. And there is, so the speed up are more or less 100 compared to single CPU, of course, at this point. But so this is, you may decrease it to 5 times if you are honest. But anyway, I mention it because I spent like half a day converting the code from CPU to GPU. So I had a single CPU code. I just sat down and I completed my CUDA kernels with some other. I had some experience with that, but doing CUDA kernels was pretty easy. So we converted the code to 100 times faster just by one day. And this is interesting. So we didn't spend a lot of time for that. And to just compare and mention, SPH also scales well, but it has to be larger. So if you don't spend enough time to actually organize your code for GPU, you have to have like more than 10,000 particles to get some nice speedups with smooth particle hydrodynamics. And so the next step we did was to get some experience with Lattice Boltzmann in real time because it scales so nice. Now what you see is an implementation of Lattice Boltzmann. This is not entire code, so don't be so that happy because it's like just a snippet of it. It shows the very basics of compute shader in OpenGL 4.3. So we implemented Lattice Boltzmann in the graphics pipeline using computer shaders, and there you have it done in an interactive way. It is done on very large grid, so it is not visible there, but it's like 640 times 320. It's a pretty large grid, and it works interactive. You see the user is now, so it was me actually, is playing with this little dot and just changing these boundaries. And the response is very nice. So you see the immediate response of the fluid flow. And the 3D is straightforward. I won't go into much details. You just get your two-dimensional grid and you convert all this to more velocity directions. You put your particles and you solve it. This is also interactive. You see the flow, and this is the same effect. So now you see the same tree, but in 3 dimensions. So let's finish with something else. Let's leave the Lattice Boltzmann. You get bored enough, but you basically hope you know the method. It's there, is around. People are using it. You may also get some free surface effects and so on. I didn't go into details of it, but yeah, you may do some research about it later on also. Anyway, there is another one, the aerodynamics. And I'm very happy to be there to describe it because it's hopefully attracts some people to do it at home because it's very simple. So the nice thing about this aerodynamical model is that we basically skip Navier-Stokes. Okay, we skip the momentum dynamic part. Okay, we leave only this continuity equation. So I'm not a liar, but I told you it will be real-time fluid dynamics. So I hope to show you some dynamical effect with this model. But so let's go. How to do that? So this continuity equation has analytical solutions. What does it mean? That means we may have some solutions of the flow which are actually fulfilling this law. That means there are some very basic fluid flow problems that are described by continuity equation. These are, for example, free flow. So this is a flow from the left-hand side to the right-hand side. It's a flow which is described simply by the velocity is equal to 1, for example, and this is the fluid flow problem solution, very simple one. There is another, the vortex flow, which also fulfills the continuity equation. And if we combine those two, we get the fluid flow like that. And there is a paper from 1991 which describes wonderful method of animation aerodynamics, which at this time was not possible in real time, and nowadays it is very possible. And I want to show you how it works. It's on today hardware. So we basically are able to get these singular solutions to the flow, combine them, and get something more fancy. And there are people who are actually working with this method in some serious applications where these single solutions are applied many times, and they describe very complicated fluid flow problems with it. So it's worth to remember something like that is around. But how to get something interesting in free flow? So we have a flow like that. We basically let it go, and it is like u equal to 1 again, and we want to have some object. So the simplest object in the fluid flow, in the computer graphics, is triangle. I have one there, so let me introduce the triangle. It's like that. Now, think about this animation aerodynamics like this. You have a triangle which we want to move in the flow. If it is oriented just directly to the fluid flow direction like that, okay, this microphone is a fluid flow vector, like this. So the force is large. This triangle will go fast. If we orient triangle like this, the force will be very low. And this is interesting because with this simple assumption, nothing more, just this is low force, this is a large force, okay? One little thing about the damping effect, but this doesn't matter. With this simple force, we can get a very nice movement. So we basically put triangles, and I will put triangles, nothing else, in the flow, and we solve the problem of the movement of this triangle with forces from the wind, okay, from this u equal to 1. I didn't put anything else in terms of fluid flow. Oh, and there is a failure attempt. So we put it, but we got like that. So there were some OpenGL problems. I wanted to show you the work was not that easy. Okay. Okay, but now we have our triangles. We put them into this free flow. We basically compute some forces on each individual particles on these triangles. So each triangle is a spring mass system model, which is then solved with simple Navier-Stokes. You may see all these effects of triangles going upwards, downwards, if they are oriented like this. If they are oriented like that, they are actually very fast pushed forward, and then they flip around, they turn, they show a lot of interesting fluid flow-like behaviors without any touch of Navier-Stokes, which is worth to remember. And then how about collisions? We now working, and this is a work in progress, with some attempts to use distance functions, so very famous on NVScene, to get some collision responses and to actually improve the fluid flow solutions we put into the system, because distance functions have also nice properties of being smooth and so on with some objects. And there is a work in progress result of triangles put in a fluid flow system with an object which is represented by a distance function, the simplest one, of course. But what is nice is that these objects collide with this, and yeah, so this is the effect. And now to summarize, there are 3 messages I want to just leave you with after this talk, because I know this was 40 minutes, not enough to really go deep into each of these solvers and problems. There are Lagrangians and Eulerian flow solver, so they exist. There is not only smooth particles, which is wonderful, and I agree this gives a lot of nice particle effects, but there are some applications we want to have bulk flow solutions. And for this, might be better to use Eulerian approach, okay? Doesn't have to, but might be. The kinetic-based theory, Lattice Boltzmann, is worth trying. There are many things I didn't show you, like multiphase and physics and so on, so that the Lattice Boltzmann is capable of doing. And the Navier-Stokes might be not necessary sometimes. And this was the animation aerodynamics I give you some few words about. I want to thank to many people there who were actually helping me out, especially my beautiful wife Claudia, who is now watching us, and then NVIDIA for making the NVScene again. This is wonderful. And thank you very much for your attention. I'm very happy to get some questions.
So if you have questions, just raise your hand up. I have a mic here. Anyone?
Could you give a word about the movie we're watching now? That animation, the last one you show, the background. No.
Ah, background. Okay. Yeah. The background one. This one.
Yep.
Okay, so this is the Lattice Boltzmann also. It's a multi-phase model, the basic one, Shan-Chen model, implemented on compute shaders also. It's, it's also in real time. Just what you see is animation to make it nice at presentation. So it's a very large grid again, and it's, so. And this is very hard to do with some other things. So Lattice Boltzmann is famous for this one also.
So thanks for the inspiring talk. I'm wondering if you use Lattice Boltzmann for water simulation. How can you create or track the free surface there?
Okay, there are many. There are two attempts in Lattice Boltzmann you may use. One is this one actually, because this is the multi-phase solution. So you have multi-phase fluids. You basically solve the fluid and air part, and if you get a fancy Lattice Boltzmann model, you are able to get the density ratio up to some few thousands. So if density ratio between this part, which is red there, and the white part is high enough, you get some kind of free surface flow. So the one way would be to track the density surface between those two phases. And it's a very nice approach, because then you don't have to go into many numerical problems with surface tracking. Another one is to use volume of fluids, use level sets, or use marker particles. Everything is possible. There are models for level sets, there are models for volume of fluids, and they are successful. I didn't talk much about it, but there is a direction into that also. Yeah.
Anyone else? I guess not. In that case, thank you, Maciej.
Thank you very much.
We'll continue in about 10 minutes with the next seminar. And also, if you have competition entries for Android demo or ANSI ASCII, please enter it now because there's deadline.